Jai Hind. Welcome to the class of Microwave and Radar Engineering. The subject code is KEC074. This is lecture number 8 and here we will continue with the modes of the rectangular waveguide. In the last lecture we have discussed about the TM mode in the rectangular waveguide, and here we will continue with the TM mode for the rectangular waveguide, and also we will start with the TE mode of the rectangular waveguide. Clear? So in the last lecture we have discussed that in the TM mode, as we know that in the TM mode, in this electric field, magnetic field in the z direction is equal to 0 and electric field in the z direction is not equal to 0. That's why it is known as the TM mode. So in the last lecture we have discussed or we have derived the general solution for the rectangular waveguide for the TM mode, that is Ez comes out to be A1 cos bxx plus में A2 sin bxx plus में multiply में A3 cos ay into में y plus में A4 sin y ay into में y e के minus gamma z. So here A1, A2, A3 and A4 are the constants. On applying the for the rectangular waveguide, as we know that for the rectangular waveguide, see this one is the rectangular waveguide. Let's say this goes continue, and let's say if I say this has a dimension a and here coordinates are 0, 0, 0, and this waveguide has this dimension is b and here its coordinates are will be what? If I say this is y, if I say this is x, so here coordinates will be 0, b, 0. Clear? And or you can say this is common known as can be act as a z, and similarly here coordinates will be what? A, 0 and similarly z. Clear? So on applying the boundary conditions, first for the first wall, when x equal to 0, y equal to 0, we will get the some values, and on the second wall we will put when x equal to a, y equal to 0, and for the third wall what? When x equal to y equal to b and x equal to 0, and for this one x equal to a and y equal to b. So at x equal to 0, Ez becomes equal to 0. So here Ez, when x equal to 0, Ez becomes equal to 0, therefore a coefficient a1 comes out to be 0. When a1 comes out to be 0, we will get the, on putting this a1, so this coefficient becomes equal to 0, we will get this solution. Now on putting for the second wall, on putting at y equal to 0, for putting at y equal to 0, Ez a3 comes out to be 0, this a3 comes out to be 0, and on putting the a1 equal to 0 and a3 equal to 0, we will get the this equation. Clear? Multiply में A2 and A4. Clear? Now see this A2 into में A4 and that is written as E0. Clear? Now on putting the third boundary condition, that is when x equal to A and when x equal to A, means at this point when x equal to A. Now when x equal to A, just put this equation when x equal to a, we will get the bx comes out to be m pi by a. This we have already derived in the last lecture also. And on putting y equal to b, here for y equal to b, Ez equal to 0 and sin ky into में b equal to 0, that is comes out to be ay comes out to be n pi by b. Just on putting this value bx and ay here in this equation, we will get the overall equation that comes out to be this one. Ez equal to E naught sine of m pi x divided by a multiply में sin of n pi y by b into में e की power minus gamma z. Now we will put the value of Ez in equation for Ex, Hx, Hy and Hx. Ex, Hx, Hy and Ey. Clear? Now when we are putting the value of Ez in this equation for the Ex, we will get the Ex comes out to be minus of gamma m pi by h square into में a e naught cos pi m pi x divided by a into में sin n pi y by b. Clear? Similarly, hx comes out to be this one and ey comes out to be this one and hy comes out to be this one. Now see, for the TM mode, there are two types. There will be a non-propagating modes and also propagating modes. Now see, non-propagating modes are the modes which will not travel inside the rectangular waveguide, which will not exist inside the rectangular waveguide. Now just see, first is TM 00 when m equal to 0 and when n equal to 0. On putting m equal to 0 and n equal to 0, here we will see that Ex comes out to be 0, Ey comes out to be 0, Hx comes out to be 0, just put this value n equal to 0, and here Hy when m equal to 0, Hy comes out to, all components of fields, all components fields will comes out to be, that's why TM 00 does not exist in the rectangular waveguide. Now see, TM 0 m can have any value 1, 2, 3, 4, but when n equal to 0, this field also does not exist. How? Now see, when I am putting n equal to 0, when just put this value and n equal to 0 here, Ex comes out to be because sin 0 equal to 0, Ey comes out to 0 because n equal to 0, the whole equation comes out to be 0. Now in Hx, put n equal to 0, here n equal to 0, Hx comes out to be 0, and for Hy, m equal to n equal to 0, put this value, the whole comes out to be 0. So therefore, in this also, the whole field components will also be a 0. Clear? Now see, when m is equal to 0, n can have any value. So that's why also in this also, all components will also be 0. Now see this one how, m equal to 0, Ex comes out to be 0, Ey में m equal to 0, sin 0, 0, Hx sin 0, 0, Hy, the here m equal to 0, the whole. Therefore, in this also the whole field components comes out to be 0. That's why these modes are known as the TM non-propagating modes. That is, generally the question is asking why TM 00, TM 10 and TM 01 does not exist inside the rectangular waveguide. Now, what are the propagating modes? Apart from this value, so I can say that TMM mode will exist when m is greater than or equal to 0, with also that n is also be greater than or equal to 1. Both should be greater than or equal to 1. So the first fundamental mode here is what? TM 11. M equal to 1, minimum value of m, that is 1, n equal to minimum value is 1. Therefore, TM mode, TM is 11. Clear? Now see, for the TE mode, the general solution comes out to be Hz equal to, similarly for the TE mode, general solution comes out to Hz equal to A1 cos kx x प्लस में a2 sin kx इंटू में x प्लस में a3 cos ky इंटू में y प्लस में a4 sin ky इंटू में y. Now on putting the same boundary conditions here, put the same boundary conditions for the first wall, second wall, third and fourth. For the first wall, you will see that from through here to here, x varies from what? 0 to a and y equal to 0. Here you will see that through this wall, x equal to what? A and y vary from 0 to b. For the third wall, you will see that here that y equal to b and x varies from 0 to a. And similarly for this one, when x equal to 0 and y vary from 0 to b. Clear? 0 to b. Now on putting this value, on putting the boundary condition at x equal to 0, that when x comes out to be 0, you will see here that a2 comes out to be 0, and when at y equal to 0, the a4 comes out to be 0. On putting this value, we will get the hz equal to this equation. Now on putting the third boundary condition, the fourth, when x equal to a, third boundary condition, you will see that on putting this value here, sin kx into x into a, because x equal to a, del z, del hz by del z, del x equal to 0. Here putting this value, just you will see that kx comes out to be m pi by a, and similarly at y equal to b, ky comes out to be n pi by b. Clear? So therefore hz, this equation comes out to be this one, hz equal to h naught cos of m pi by a into में cos of n pi by b multiple में by e के over minus gamma z. Now put the value of hz, putting the value of hz in equation for ex, hx, hy and ey. Now on putting the value of hz in ex, hx, ey, hy equation, we will get this. Ex comes out to be this one, hx comes out to be this one, and ey comes out to be this one, hy comes out to be this one. Clear? Now see what will be the non-propagating modes here. See, when both are m equal to 0 and n equal to 0, when both m equal to 0 and n equal to 0, this is a non-propagating, means this mode will not exist inside the rectangular waveguide. Clear? So on putting m equal to 0 here, put the value of m equal to 0 here and n equal to 0, ex comes out to be 0, m0, ey comes out to be 0, m0, hx comes out to be 0, here n equal to 0, hy comes out to be 0, means all field components are 0 except hz is not equal to 0. That's why T is 0 0 mode does not exist inside the rectangular waveguide. And what are the propagating modes? Propagating modes are the modes that is T is 0 1 0 n, n should be greater than or equal to 1, T m0 where condition is m is greater than or equal to 1, and T mn when m is also greater than 1 and equal to greater than 1. These are the propagating modes. Clear? Now see, we will calculate what is the, or we will tell you that what is the dominant mode in the rectangular waveguide. Clear? Now see, first, as we know that here gamma is what? Propagation constant, and from the derivation equation, from the derivation we have seen that the h square equal to gamma square plus में k square. Both are the propagation constant. Now, and this h square is also equal to what? K square x into में plus में k square y. Therefore, gamma comes out to be what? Equal to under root of k square x plus में k square y minus में k square. Now, the first case is one. First, this gamma is what? Propagation constant. This gamma is what? Complex number, that is alpha plus में j beta. Now, the first condition is when gamma equal to alpha. Now, when I say that gamma equal to alpha, means imaginary part will not be there. And when I say that the imaginary part will not be there, it means that k square x plus में k square y should be greater than equal to k square, means this equation should be greater than 0. Or I can also say that, therefore I can say that the omega square, this is what? K square x is what? This one. K square y is 1. This one. So I can say, and what is k square? K square is equal to what? Omega square mu epsilon. Therefore, omega square mu into mu epsilon should be less than m pi by a square, that is equal to what? Kx, that is equal to k square y. Clear? So this condition is, when this condition exists, in that case the evanescent field exists, evanescent field will be there. It means that there will no complex number, means there is no imaginary part, only alpha. Alpha is what? Attenuation. Clear? Now, what is here? In this case, the only attenuation will exist, means there will be no propagation. Now, when I have to say the propagation exists, when there is I say then propagation exists, in that case alpha equal to 0 comes out to, and only j beta will be there, means gamma comes out to be j beta. When gamma, I say gamma equal to j beta, I can say that the k square x plus में k square y should be less than the k square, or I can say that the k square x plus में k square y minus में k square should be less than 0. So put the value omega k square is equal to omega square mu into mu epsilon should be greater than equal to this one. Now, omega is what? 2 pi f. Therefore, f comes out to be this one. So, for the propagating mode, for the propagation, frequency of the mode should be greater than 1 upon 2 pi under root of mu into mu epsilon under root of m pi square by a square plus में n square pi square by b square. Clear? Now, if I say what is the minimum frequency for the propagation of wave, it means that f should be equal to this one, or I can say that the k square x plus में k square y should be equal to k square. Therefore, gamma equal to 0, k square x plus में k square y should be equal to k square. That comes out to be cutoff frequency, that comes out to be this one. So, this is the least minimum frequency above which the wave will propagate, because above which this will be there and then this propagation will be there. So, this is the minimum cutoff frequency, and this frequency above which all frequency or modes will propagate. Means the mode which exists, which have a frequency greater than fc, that mode will propagate inside the volume. Clear? Now, when I say on solving this equation, you will also take a pi square common. You will see that the 1 upon 2 pi under root of mu into mu epsilon m square by a square plus में n square by b square. Clear? So, fundamental mode is the what mode? Fundamental mode is the mode with lowest cutoff frequency. For TM mode, it is TM11, and for the TE mode, it is TE01 or TE10. Clear? Condition, that depends on the condition, what is the dimension of A and B. Generally, what? A is greater than B. So we will see that the TE10 will be the dominant mode. Clear? Is it clear? Now see here this one also. See this one. This is for the TE mode. The lowest cutoff frequency, that is 3 gigahertz, above which all frequency will propagate inside the, above which the all signal or signal having a frequency greater than 3 gigahertz, all modes will propagate inside the wall, inside the rectangular waveguide. So this is the what? Dominant mode, and this is dominant mode is what? TE10. Here condition is that A is greater than B. Clear? And you will see here TE01 will also have a frequency greater than 3. Therefore TE01 is not a dominant mode. Is not a dominant mode when A is greater than B. TE01 is a dominant when B is, when B is greater than A. Clear? And this condition when A is greater than B. Clear? So these are the modes above which exist inside the rectangular waveguide, which having a frequency greater than the cutoff frequency. Clear? So degenerate modes are the modes with same cutoff frequency, TM11 and TE11. Clear? So these modes have the same frequency, and TM21 and TE21, these are also having same cutoff frequency, and TM31 and TE31, they both are having a same cutoff frequency. That's why it is known as the dominant degenerate modes. Now see here, what is phase constant to the intrinsic impedance? This is gamma, as when phase constant will be what? Beta. Beta, it comes out to be this one. So beta is, as we know that what? Fc is what? This one. So just put this value here. Fc is what? On putting this value omega square, this one, you will get beta is what? 2 pi by lambda. 2 pi by lambda. Clear? On putting this value, you will get the beta comes out to be omega into me root of mu into me epsilon and root of 1 minus me Fc by F ka whole square. Clear? Now what is intrinsic impedance? Intrinsic impedance for the TM mode, that is Ex upon me Hy, or equal to minus of Ey upon me Hx. On putting the value of Ex and Hy, here you will get this one, intrinsic impedance for the TM mode, and for the TE mode the intrinsic impedance comes out to be this one. Putting this the value of Ex and Hy from this equation, putting the value of Ex and Hy, I'll get this equation, and on putting the value of omega beta from this one equation, put the value of beta from this equation here, you will get this one. Clear? Similarly, the phase velocity is what? The velocity with which phase changes, that is the phase velocity, that is Vp equal to, comes out to be omega by beta, that is V upon me under root of this one. Group velocity, the velocity with which whole group, means whole envelope travels, that is Vg equal to d omega by d beta, that is equal to, on putting this value, you will get V equal to this one. So therefore this is the equation, Vp multiply by Vg equal to V square, V is equal to speed of light. Clear? Now taking example, let's see numerical. For an airfield rectangular waveguide WR430, means this having a some basic dimension, that WR430 means A is equal to 4.3 inches, that comes out to be, that is equal to, multiply my convert inches into my centimeter, that is comes out to be 10.922 centimeter. And where when I say WR430 means B is what? A by 2. B equal to A by 2. So this one. So find the cutoff frequency in TE10 means M equal to 1, N equal to 0. Fc equal to this one. I have already told you. Put M equal to 1 for the TE mode, TE10. M equal to 1, N equal to 0. Put the value of M equal to 1 here, N equal to 0. You will get, this is the cutoff frequency. And for the TM21, put the value of M equal to 2 and N equal to 1. I will get the cutoff frequency for the, that comes out to be 3.884 gigahertz. Clear? Second part is, if the waveguide is filled with a dielectric constant, that is epsilon r. So when I am putting this epsilon r, here I will get what? That is equal to epsilon r C upon by twice of under root of epsilon r into this one. Means here I comes out to be this one. Clear? On putting this value, you will get this equation. That is, for the TE10 mode, the cutoff frequency is 0.925, and for the TM21, 2.619 gigahertz. Now next example is, the dominant mode in a rectangular waveguide is TE10. We know that because this mode has what? I know that the dominant mode in TM rectangular waveguide TE10 because of no attenuation, no. Option R, no attenuation, no cutoff, no magnetic field, no the highest cutoff frequency, highest cutoff wavelength. Dominant mode exists what? Which having a lowest cutoff frequency. When I say this is having a low cutoff frequency, in terms of it is what? High cutoff wavelength. Because I know that the frequency is inversely proportional to lambda. That's what dominant mode. This mode has the lowest cutoff frequency and the highest cutoff wavelength. That is this one. The option is D. Clear? So these are all options are wrong. Now next question is, the phase velocity of a TE10 is in an air-filled rectangular waveguide is less than C, equal to C, greater than C, or none of the above. As we know that the Vp is equal to what? Phase velocity is equal to greater than is C. That is, C is what? Under root of on putting this value, I will that the phase velocity is always greater than the. Next question is, which of the following statement is having a fundamental frequency of the metallic waveguide? In basic, which of the following have the fundamental mode? As we know that this is a coaxial mode. This coaxial mode has a TEM mode, and these are the cylindrical waveguide, and this has a rectangular. These both modes have a TM mode and TE mode. Clear? Only P options are, only P has no cutoff frequency, only Q has no cutoff frequency, only R has no cutoff frequency, and all three have cutoff frequency. As we know that for the TEM mode, there is no cutoff frequency. No cutoff frequency will exist for the TEM mode. So therefore the option will be T mode, and this both having a cutoff frequency. TM mode and T mode both having a cutoff frequency. That's why it is known as the. That's why the only option A is correct. Only P has no cutoff frequency. So that's all for the today's lecture, and we have concluded the rectangular waveguide for both the TE mode and the TM mode. The book I have referred for preparing these slides is SM Lyo, Microwave Devices and Circuits by SM Lyo. Thank you.